Good morning. So we're just going to wait maybe a minute for people to join. Hassan, are you there? Hassan Meliani? Just say here on the mic. Hassan, can you just turn on your mic for a second? Just say here.
Yes, good morning, Professor.
You here?
Yes.
Okay, thank you. Okay, you weren't here last class, so I've got you here now on the attendance. Okay, so Hassan. Meliani. Maida. Okay, good. Good morning. Okay, that's great. So that means I have everyone on the attendance. So everyone in the class is now present, marked present. Okay. Okay, so that's good. Okay, good. Okay, so we don't have to waste time on that anymore. Okay, good. Sorry about that. Okay, so so good morning. Welcome to the second class. You should see Word on the screen now. So let's continue where we left off. So last class, I introduced the class, introduced the course. We also talked about definitions of probability. Right? So four definitions of probability, right? You have classical probability, empirical probability, surjective probability, and axiomatic probability. So we had four definitions of probability. Okay, and we had an example of classical probability, right, with rolling a dice, right? So probably rolling an even number is 3/6, right? So we had an example of classical probability, and we started talking about empirical probability. And so we talked about empirical probability. Okay, so that's most of the material we covered last class. Okay, so this class, we're going to talk about, again, the drawbacks of empirical probability. We're going to talk about subjective probability. Okay, we're going to talk about axiomatic probability. And we're going to talk about set theory. Well, we're going to talk about experiments, outcomes, sample spaces. Okay, and then if there's more time, we may talk about set theory also. Okay, and so and then set theory if there's time. Okay. Okay, so that's the plan for this class. So let's get started. So last class we talked about empirical probability, right? And I gave you the definition of empirical probability. Right, so the definition was if S is an experiment with unpredictable outcomes, and if A is one of the possible outcomes of S, then we say that the empirical probability of the outcome A is the number P if, in repeated performances of S, the long-run relative frequency ratio of occurrences of A tends to the number P, right? So it was a really long definition, and we talked about it. So a few problems with the definition of empirical probability, right? So one, you cannot repeat an experiment infinitely many times, which the definition requires to get the exact value of the probability in the definition. Okay, right? And then even if you repeat an experiment infinitely many times, you can get different results, right? Right. So just because you do manage to do the experiment infinitely many times if possible, you can get different results, which means you could technically get a different limit, a different probability from the experiment. Right? And if P, the probability, is approximately n sub A over n for large n, right? It is not clear how large little n needs to be, right? So you take n sub A over n for, a large n. If you repeat the experiments enough time, n sub A over n should be near the probability P. But you could ask the question of how large does little n need to be? How many times do you need to do the experiment to get a good approximation or actual value? And so that's unclear, right? So these are three problems with empirical probability. Okay, so that finishes empirical probability for now. And so the next thing to talk about is subjective probability. Okay. So start with the definition. So subjective probability is the personal evaluation of the likelihood of chance phenomena. Okay, so subjective probability is the personal evaluation of the likelihood of chance phenomena. So an example of that would be if you said, it is definitely going to rain, right? Like it was raining last night. So if you were saying it's definitely going to rain, you're saying it's 100% certain. You are 100% certain it's going to rain. Right? That might be an opinion, right? You may not know for sure it's going to rain. You think it's going to rain. Okay, so it's about a personal evaluation. A better example might be, the Mets. If I said I believe the Mets are going to win the division, right? So this is a subjective probability, right? Right. Well, I believe the Mets have a 70% chance of winning the division, right? So I'm making a personal evaluation of the likelihood of them winning. I don't know. It's not based on any kind of math, right? It's just a subjective, it's just an opinion-based probability. That's subjective probability. Okay. And so it might seem like this definition of probability is silly or ridiculous or has no value, but in reality, in life, we don't know the odds of many things happening. And sometimes, even when we infer the odds of things happening, we have to assume that the likelihood of other things happening that we don't know. So, we might make a subjective estimate of what the likelihood of something is, and then deduce from that the likelihood of something else. So, subjective probability does have some value. Okay. Okay, so that's the idea of subjective probability. The next one is the axiomatic definition of probability. Okay, so it is a definition based on axioms. And so what axioms are statements of minimal requirements for a definition of probability. Okay, so axioms, right, are a collection of assumptions that you make in order to build the field of probability. Okay, now you want these assumptions to be minimal. You want to assume as little as possible and create as much math as possible, right? If you assume too much, if you assume everything, then you're not really concluding anything, right? If you assume the entire field of probability, then you don't really done anything. So you want to assume as little as possible, and then from that create as much math, as much probability as possible. So that's the goal of the axiomatic probability: to assume as little as possible and to figure out as much as possible from it. Okay. So that's axiomatic probability. Okay, so it allows for the rigorous development of the math of probability. Okay, and because the axioms are well chosen, it is essentially the same as the other definitions. Okay, right? So you can assume whatever you want, right? Some assumptions are good assumptions, some are bad, right? But the assumptions in axiomatic probability are specifically chosen so that the math you get, the probabilities you get, correspond with classical probability, subjective probability, empirical probability, right? If you flip a coin and you start looking at the odds of getting heads, that matches up with the axiomatic probability, right? And so we could have made probability anything we wanted. We created it so that it would match, what we want it to be, what our intuition, for the most part, tells us it should be. Okay. Okay, so that's that one. So here's an exercise. Okay. The exercise is it classical, empirical, or subjective? Okay. So I'm just going to give you a scenario, an experiment. And what I want you to do is to tell me whether it's whether it's an example of classical probability, empirical probability, or subjective probability. Okay. So give a minute for people to think about it. The first one is a box has 10 balls. Has 10 balls. 3 are red. 3 are red. Okay. The probability of drawing red is 3 out of 10, which as a decimal is 0.3. Okay. So the question is it an example of classical probability, empirical probability, or subjective probability, and why? Okay, so can someone answer that for me? Because you can turn on the audio and just say the answer. Anyone? Jamil, do you want to answer it? I see like a light around Nora Med. I don't know why there's lights and stuff. Okay, so nobody wants to answer it. So it's classical probability, right? It's classical probability because, right? So it's not subjective, right? It's not an opinion-based one. It's not empirical either because you're not actually drawing the balls, right? Empirical probability would be actually doing the experiment. Here, you just have 10 balls, 3 of them are red. You just look at it and you say, okay, the probability of drawing red is 3/10, right? That's classical probability. Okay, so this is classical probability. Okay, so you do not actually perform the experiment, right? The probability is not based on your opinion. Okay. The second example is 2,000 tosses of a certain coin results in 1,200 heads. Therefore, the probability of heads is 1,200 out of 2,000. And 1,200 out of 2,000 is 60% or 0.6. Okay. So the question is this classical probability, empirical probability, or subjective probability? So which one is it? Right, classical probability we see in 1, right? That's an example. Subjective probability is based on your opinion. Empirical probability is doing the experiment and getting the probability from the experiment. Okay, so 2,000 tosses of a certain coin results in 1,200 heads. Therefore, the probability of heads is 1,200 over 2,000, which is 60% or 0.6. So which type of probability is it?
Wouldn't it be empirical probability because you're physically doing the experiment itself and then getting your answer?
Yeah, this is Hess' name?
Yes, yes.
Okay, did I say your name right or no?
Yes, you said it right.
Are you sure? Okay, so yeah, that's correct, Hess' name. Okay, so yeah, you do the experiment, and so it's empirical, right? So empirical is easy to spot, right? So this is empirical probability. So you perform the experiment and get the probability from it, right? So classical might be the hardest to see, but if you think about it, if you do process of elimination, it can be kind of easy because it's not subjective, it's not based on opinion, and well, this too is empirical. 1, there was no opinion, and you didn't do the experiment, so you can kind of you can get classical the easiest way from process of elimination. And 2, you do the experiment, so it's empirical. Okay, the third example is this. David has a certain appearance, confidence. Okay, you think he has a 75% chance, 75% probability of winning first prize in the judo match. Okay, so David has a certain appearance of confidence. He looks confident to you. And so you say, okay, I think he has a 75% chance of winning first prize in the judo match because he looks confident. So is that classical, empirical, or subjective probability?
I think it's subjective because it's like personal evaluation of himself.
Good. Yeah, you're right. You're absolutely right. So it's Kishan, right? Kishan?
Yeah.
Okay. That's absolutely right. So it is subjective probability. It's based on his opinion. David looks confident, and so then you have the opinion that he's going to win, right? 75% chance likelihood. So Yeah, that's subjective probability. Very good. This is subjective probability, right? This probability was gotten by a personal belief or opinion. Good. Okay, so good. So that makes sense, right? So that the goal of that exercise is just to be able to, see which type of probability a situation is this, is shown. Which probability each is. Okay, good. Okay, so the next section is on elements of probability. And so here we're going to just talk about some introductory topics, definitions, so that we can talk about probability. So we're going to talk about experiments, outcomes, and sample spaces. Okay, so these are three important terms to know and understand. Okay, so first, a definition: an experiment is a specific set of actions, the results of which cannot be predicted with certainty. Each possible set of recorded data defines a result called a simple outcome of the experiment. Okay, so this is definition of an experiment. And it's also, the second sentence gives you the definition of a simple outcome. Okay? So an experiment is a specific set of actions, the results of which cannot be predicted with certainty. Each possible set of recorded data defines a result called a simple outcome of the experiment. Okay, so let me use the same example for this. Let's say you roll a fair or balanced, meaning the same thing, six-sided die, right? And you record a number on the top face of the die, right? So when you roll a die, there's a number on the top face facing upward, and that's the number that you think you consider as being the number rolled, not the number on the side, right? So let's say you do that, right? In this situation, the experiment is rolling a fair six-sided die, right? And so it's an experiment because it is an experiment because you cannot predict with certainty which number will be at the top, right? So this is an action with an uncertain result, right? So rolling a die is an action with an uncertain result. And so rolling a fair six-sided die is an experiment. Okay. Now, a simple outcome of this experiment is, well, you record the number on the top face of the die every time you roll it. And so the definition says each possible set, I should say simple outcomes of this experiment. So each possible set of recorded data defines a result. Okay, so the simple outcomes of this experiment are all of the possible numbers that can appear on the top face of the die. So that's 1, 2, 3, 4, 5, or 6. Okay, so those are the 6 simple outcomes of the experiment. Okay. All right, so let's do now a more specific example 1.1. So let S be the following experiment. Roll a die and roll a red die and a green die and record the value on the top side of each die. Okay, so this is our next experiment. And so you can use a variable to represent the entire experiment. So instead of, if I were to talk about this experiment again, I wouldn't have to describe the entire thing. I could just say experiment S, right? Because I said here, let S be the following experiment. Roll a red die and a green die and record the value on the top side of each die. So now every time I refer to the experiment, I could say experiment S instead of the entire sentence. Okay. So here, the goal is going to be to write down all of the simple outcomes of this experiment. Okay. So you roll a red die and a green die, and they're fair, balanced dies with numbers 1 through 6 on each. Okay. So the goal is to write down all the simple outcomes of this experiment. Okay, so if the value on the red die is I, and the value on the green die is J, then the ordered pair I comma J is a simple mathematical notation for this pair of values. Okay, so I comma J is saying, okay, well, in the first thing here, that's telling me the roll on the red die, and the second number is going to tell me the roll on the green die, right? And for an ordered pair, it's a way of talking about two things, and order matters. And so there's a clear difference between the first coordinate and the second coordinate. The first coordinate corresponds with the value in the red die, and the second coordinate corresponds with the value in the green die. Okay. Okay. So thus, each ordered pair I comma J for all the values I, which equals 1, 2, 3, 4, 5, or 6, and J equaling the values 1, 2, 3, 4, 5, and 6, represents a distinct simple outcome of the experiment. Okay, and so conversely, each distinct simple outcome of the experiment is represented by some ordered pair I comma J that I just listed. Okay, so the ordered pairs I comma J, where I ranges from 1 to 6 and J ranges from 1 to 6, each ordered pair represents a distinct simple outcome of the experiment, and every distinct simple outcome of the experiment is attained or represented by one of these ordered pairs. Okay, and so our conclusion on all of that is that the complete list of simple outcomes of this experiment, or of experiment S, is the following. So if I were to list all of them, then I would say, okay, you have 1, 1, you have 1, 2, you have 1, 3, you have 1, 4, you have 1, 5, you have 1, 6, right? And then, you have 2, 1, 2, 2, 2, 3, 2, 4. I'm not going to do all of them. 2, 5, 2, 6. Okay, and then the pattern continues, right? And then finally, we have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Okay, so the ... means in between are the ordered pairs with first coordinate 3, 4, and 5. Right. Okay, so these are all the simple outcomes, including all the ones in the ... all the simple outcomes of this experiment. So this list has a total of 36 simple outcomes of the experiment. Okay, so there's 6 rows and then 6 columns, right? 6 times 6, 36. Okay, so what this shows is that all of the simple outcomes of this experiment in that list, there are in the list, and there's 36 of them, and they're all distinct. Okay. Okay, so another definition, a sample space is a non-empty set of elements. A set S is a sample space for an experiment capital S if each element of capital S represents a unique simple outcome of capital S, and if each simple outcome of capital S is represented by a unique element of capital S. Right, so a sample space is a non-empty set of elements. A set capital S is a sample space for an experiment capital S. Oh, I saw it happening. Okay, so I got loose ones here. So, so definition: a sample space is a non-empty set of elements. A set S is a sample space for an experiment. I'm going to call it E. If each element of S is a unique simple outcome of E, and if each simple outcome of E is represented by a unique element of S. There we go. Okay, so the elements of capital S are called sample points. There we go. Okay, so here's the definition of a sample space. This is a definition of sample points. Okay, so I'll read it again. A sample space is a non-empty set of elements. Simple. And a set S is a sample space for an experiment E if each element of S represents a unique simple outcome of E, and if each simple outcome of E is represented by a unique element of S. The elements of S are then called sample points. Okay, so if the experiment, right, if the experiment is roll a fair 6-sided die, right, and record the top base value, right, then sample space, well, it's a non-empty set of elements, right? So the sample space should just be 1, 2, 3, 4, 5, and 6 in a set. Okay, so this, I'm going to call this set S. Okay, so here S is a sample space for experiment E, for the experiment E. And so I'm going to call this experiment E here. Okay. Okay, so each element of the set S represents a unique simple outcome of the experiment E, right? Each of these numbers is a unique simple outcome of that experiment. And each simple outcome of the experiment is represented by a unique element in the set. Okay, so those two things happen, and so this is a sample space for that experiment. Okay. Now the experiment in example 1.1 with this list of ordered pairs, right? So the experiment 1.1. So for that one, the sample space, capital S, well, so the sample space here, remember we listed the outcomes of the experiment, right? It was these 36 ordered pairs, right? But you don't want to write 36 ordered pairs. So instead, you can write it like this. It's the ordered pairs I comma j, such that 1 is less than or equal to I and j are between 1 and 6 inclusive. Okay, so this is a sample space here. This is sample space S for experiment 1.1. Okay, and so you read this equation above as the sample space S is equal to the set of all ordered pairs I comma j, such that I and j are between 1 and 6 inclusive. Okay, so that's how you can say this equation in words. Here I wrote sample space S equals that. And so you could read this as sample space S is equal to the set of all ordered pairs I comma j, such that I and j are between 1 and 6 inclusive. Okay, so there's two ways to quickly, succinctly describe that sample space of 36 ordered pairs. Okay. Okay, so okay, good. So I will also use the whiteboard here. So I'm going to now go to the whiteboard for a minute. So we represented the sample space as that set, right? The set of all ordered pairs I comma j, such that I and j are between 1 and 6, right? So you can also represent a sample space, not just as a set, you can represent it using a graph. And so I'm going to illustrate that graph here on the whiteboard. Okay, so you should be able to see the whiteboard now. Okay, so yeah. Okay, so there's the x-axis and y-axis. So here, I'm going to put the values on the red die. So this is the value of the red die. And so the values of the red die could be 1, 2, 3, 4, 5, or 6. And then the value on the green die, so this is the green one. So the values in the green die could be 1, 2, 3, 4, 5, or 6. Okay, and so so this is a graphical representation of the sample space earlier. So you could have 1, 1. Okay, that didn't work. Okay. Okay, so just let's do it like this. And so you have a point here, a point here, a point here, 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 and here. Right, so you get it, right? So you have 36 points, and these 36 points represent the 36 elements of the sample space. Okay, so these are the 36 elements of the sample space, values on the red die and value on the green die, right? So for instance, this point would represent the ordered pair 6, 6. Right, so that ordered pair represents 6, 6, 6 for the red die and 6 for the green die. And you know, like this ordered pair is 2, 1. And that represents a value red, the 2 on the red die and 1 on the green die. Okay, so each of these 36 points correspond with 36 ordered pairs, and those 36 ordered pairs each tell you the value on both die. Okay? And so that's a graphical representation of a sample space. Okay, so you see you can represent a sample space in words, you can represent it as a set, you can also represent it as a graph. And so there's multiple ways, there's many ways to say the same thing or illustrate the same thing, and that's shown in this situation. Okay, so let's look at another example. So this is example 1.2. And so here we're going to define a sample space for each experiment. So the first experiment is toss a coin and record the face on the top side of the coin. Okay, so I actually already did this one. So then S here, the sample space is just, you know, 1, 2, 3, 4, 5, or 6. Right? And the second experiment is draw a card and record the suit of the card drawn. Right? This is a standard 52 card deck, right? And so just quickly, I'm just going to describe a standard 52 card deck. And so a standard 52 card deck consists of 13 values. Okay, so there's 13 values in the deck. And so these values are the eighths, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Okay, so that makes up a total.
Excuse me, for the example, the example 1, right? When you toss a coin, it's heads and tails. So why does it go up to 6?
Oh, my bad. Okay, right. So it's heads or tails.
Okay, just wondering. Sorry.
Okay, there we go. Yep. Okay, so you toss a coin and record the. Good. Okay, so yeah. So when you toss a coin, it just misspoke. So it's either heads or tails, right? The top side of the coin. Okay, for 2, draw a card and record the suit of the card drawn. So I'm just quickly going over what the 52 card deck consists of. So there's 13 values, right? Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. Those are 13 values. Each of the 13 values okay, so each of the 13 values has 4 suits, right? So there's 4 suits. And so each of the each of the 13 values has 1 card in each suit. Okay, so the 4 suits are spades, hearts, diamonds, and clubs. Right? Okay, so so there's 13 values. Each of the 13 values has 1 card in each of the 4 suits. Okay. Now spades. Actually, so I'm going to put clubs here and diamonds like that. That's usually the order. So spades and clubs are black suits, and hearts and diamonds are red suits. Okay. So this right here is a description of a standard 52 card deck. Okay, so right between those two lines, you have the description of a standard 52 card deck. Okay. Yeah, I don't like that drawing. There we go. Okay. So again, 13 values. Each of the 13 values has one card in each suit. So if you have an ace, you have an ace of spades, an ace of hearts, an ace of clubs, and an ace of diamonds. You have a 2 of spades, 2 of hearts, 2 of clubs, 2 of diamonds, so forth. And then when you have the ace, and you have one of each suit, the spade and the club are black, and the heart and diamond are red. Okay? And so if you have 13 values and each one has 4 suits, 13 times 4 is 52. So there's a total of 52 cards in the deck. Okay? Okay, so I've already described the entire deck above, but just note that, oh, I already said standard 52 card deck. All right. So that's the description of deck. So the experiment is draw a card from a standard 52 card deck and record the suit of the card drawn. And so what we want to do is have a sample space S for this experiment. So what are the elements of this sample space? You draw a card and record the suit of the card drawn. It's a little confusing of a question, right? So mix a deck, right? And then, you ask somebody to draw a card. So that person draws a card, right? And after you draw the card, you record the suit of the card drawn. So give me an example of one thing that you could record after you draw the card, right? You have to record the suit of the card. So what's one example of something you could record from a card that you pick up?
The value?
Well, draw a card and record the suit of the card drawn, right? So you draw a card, give me one example of something you would record.
So it can be either of the 4. So it's spades, hearts, clubs, or diamonds. That's the sample space.
Okay, so you want to tell me the whole thing. Okay, so tell me the whole sample space again.
Spades, hearts, clubs, and diamonds.
Good. Good. So that's the sample space, right? The sample space is only the things that you would record in the experiment, right? And so in the experiment, it's telling you you're recording the suit of the card drawn. And so the sample space S are all the possible things you could record. That's only the suit, right? Because the experiment is telling you what matters. Okay, good. Good. Okay, so that's that makes sense, right? Okay, so then the third one is toss a coin.
Or you put.
Yeah.
So you put like a spade instead of club in the sample space. You put spade 2 times.
Oh, spades, hearts,
Club.
clubs, diamonds. There we go. Good. Okay, good. Okay, right. Okay, so those are the 4 suits. Okay. Good. Okay, so right. So the attendance, I took the attendance. Everyone is, I looked at the chat. Everyone's been marked present for the semester. So I'm not taking attendance anymore. You're all good. Okay, so you toss a coin and then roll a die, right? So and so now we want the sample space for this experiment, right? So what would be the sample space for this experiment? Give me one outcome of the experiment. It's an ordered pair. Give me one ordered pair that would describe this experiment and one simple outcome of this experiment.
Would it be heads and then like a 3 when you roll the die?
Good. Heads, comma 3, right? So the ordered pair is telling you the order. The order is telling you which thing corresponds with which. So heads is telling you the result of the toss coin, and 3 is telling you the result of the roll of the die, right? So that's one simple outcome. So what are all the simple outcomes? right? So what would be all the simple outcomes of this experiment?
Like head 1, 2, 3, 4, 5, 6. I mean, like head in each one, and then you can have tail 1, 2, 3, 4, 5, 6.
Good, and then so after heads, the next one is but after you do heads 1, 2, 3, 4, 5, and 6, then what's after that?
Tail
Tail.
1.
Good, tails. Good. So so then you have tails 1, and then next would be tails 2. Next one would be tails 3. Then it would be tails 4. Tails. No, that worked. Okay, so then it would be tails 5, and then it would be tails 6. Okay, and so that would be that. But I don't want the parentheses, I don't want like that. I want the parentheses like this. You have the parentheses. S, right, and so then just like in one line, not like that. Okay, so kind of like it's just I want the brace to start and end, right? Not putting but it's like one line, right? So it just run out of room on the page. I'm gonna lower the font for just this, like that, So maybe it could go 9. Okay, so like that, right? I'm just making it small so it all fits in one line like that. And the brace is at one end and the other end. Okay, good. So that's that experiment. Let's move on. Okay, so those are 3 examples of sample spaces for experiments. Okay, another definition. A sample space is finite if it consists of a finite number of elements. It is discrete if it can be placed in a one-to-one correspondence with the positive integers, or if it is finite. Sample spaces that are neither discrete nor finite are called non-discrete sample spaces. Okay, so a sample space is finite if it consists of a finite number of elements. So an example of a finite sample space would be rolling a fair 6-sided die, right? Because there's only 6 numbers. That's a finite amount of simple outcomes. So a sample space is finite if it consists of a finite number of elements. It is discrete if it can be placed in a one-to-one correspondence with the positive integers, or if it is finite. Okay, so if you have an experiment and you look at its sample space, right? Its sample space is discrete if it's finite. So that's one way it could be discrete. Or the sample space could be infinite. But if you can take the sample space and place it in one-to-one correspondence with the positive integers, then it's also discrete. And what does that mean, right? So putting a set, like a sample space, in one-to-one correspondence with the positive integers means that you can make the sample space into a list, an infinite list, where there's a first thing, a second thing, a third thing, a fourth thing, a fifth thing, and so forth, right? And so that tells you the size of the sample space, right? When a sample space is finite, maybe there's only 6 things in the set, or 10, or a million, or a trillion, there's finite number, right? You can assign a number to the amount of things in that set. When something's bigger than that, when something's so big that it's infinite, that you cannot say that there's a set number of things in it, the list, it keeps going, right? It's infinite, right? But there's different sizes for infinity, right? There's an infinity that's smaller, and there's an infinity that's bigger. So the smallest thing is finite. The next thing is it's not finite, it's infinite. But the smallest infinity is a list. It's an infinite list. Okay, where it's small enough infinitely that you can make into a list. If something is so big as an infinite that you can't put into a list, then it's called uncountable. Okay, so here a discrete sample space is one that can be made into a list. Okay, it would be like if you go to the grocery store and you bought infinitely many things at the grocery store, but you made a grocery list of all the infinite things you were going to buy. So first you were going to buy bread, second you're going to buy cheese, third you're going to buy eggs, fourth you're going to buy this. So you go through the grocery store and you buy all these infinite many things one at a time. So you buy one thing, the second thing, then the third thing, then the fourth thing, and so forth, but you do it forever. But you always do one, then the next. That would be an infinite that's small. And so that would be an example of a discrete sample space would be a set kind of like the list, a grocery list that never ends, where you always buy another thing. You never stop buying things, but you do one after the other. Okay. If you were to talk about the real numbers between 0 and 1, all the real numbers between 0 and 1, including, let me say between 0 and 10, you could have pi, you could have 3/4, you have pi plus 5, right? You have e times pi, right? So you have all these weird numbers in between, and there's so many real numbers that it's actually uncountable. You can't put them in a list, right? So if you try to list the real numbers, you can't. There's too many. When you make a list, there's infinitely many things between the things in the list, right? And if you try to capture them, it keeps going, right? So real numbers are an example of an uncountable set. Okay, so a discrete sample space is a sample space as a set that's finite or can be put into one-to-one correspondence with the positive integers. You can make the sample space into an infinite list. Okay? Okay, so sample spaces that are neither discrete nor finite are called non-discrete sample spaces. So if you have a sample space that's not finite and it's so big as an infinite set that you can't put the things in it in a list, then it's not discrete. It's a non-discrete sample space. Okay. So I'm going to underline this. There's a third definition there. Okay, so we define those 3 things there. Another definition. Results of experiments that are represented by subsets of the sample space are called outcomes. Okay, a simple outcome is an outcome represented by a subset consisting of a single sample point. Okay, so another definition. Results of experiments that are represented by subsets of the sample space are called outcomes. Okay, so what does that mean, right? Okay, so let's say you roll a fair six-sided die, right? What is the sample space? It's the numbers 1, 2, 3, 4, 5, or 6, right? Sample space, rolling a die, 1, 2, 3, 4, 5, or 6, right? That's the sample space. If you were to take a subset of that sample space, it's called an outcome. So let's say one outcome would be an even number. So the set 2, 4, 6 is an outcome of the experiment of rolling a die and recording the number at the top. Even numbers are the subset of the numbers from 1 through 6. So any subset of the sample space is called an outcome. Okay, a simple outcome is an outcome represented by a subset consisting of a single sample point. So when you take a subset of the sample space that consists of only one thing, it's called a simple outcome. So let's say you took the singleton set with just the number 1 in it. That would be a simple outcome. The outcome of rolling a number of 1, just 1, is a simple outcome. If you said the outcome if you had the outcome of evens, right, there's 3 possibilities. And so it's not a simple outcome. Okay. So a subset of the sample space consists of exactly one thing. This is a simple outcome. More generally, any subset of the sample space is called an outcome. Okay. So an outcome is not one possible result of the experiment. An outcome is any collection of results of the experiment. Okay. So the result of what could happen when you roll a die is that you could roll a 1, 2, 3, 4, 5, or 6. Any collection of those possibilities is an outcome. Okay. And so you could talk about the outcome of rolling an even. You could talk about the outcome of rolling an odd. You could talk about the outcome of rolling a number less than 5, right? And so outcomes are subsets of the entire sample space. It consists of more than one result. It could consist of more than one result of the experiment. Okay, good. Next is 1.3.2, which is on set operations applied to outcomes. And so here we're going to start talking about set theory, which is the study of sets, right? And so set theory and sets are kind of a building block to mathematics and how we speak about mathematics. So we need to describe something. We often use sets to describe it. Okay, so the first thing to talk about are sets themselves. So let's say you had set A. We denote the set by A, and the elements in A are A1, A2, A3, ... A sub n, right? So this set has n elements in it, A1 to AN. Okay, and so this is the set of elements A1, A2, A3, and so forth, to including AN. Okay, so that's simple, right? A set is a collection of objects or elements. Okay, here, if you have I, let's say you have the set I, which consists of the numbers 1, 2, 3, 4, ... up to and including 100. This is the set of integers from 1 to 100. Okay, and so notice how we did not write all 100 numbers in the set, right? If you're talking about a collection of things that consists of 100 objects, you don't want to write down all 100 objects. If there's a recognizable pattern that can help you describe those 100 things in a concise way, use that pattern. So here, if you want the numbers, the integers from 1 to 100, use a ... right? 1, 2, 3, 4, ... 100. And so the reader clearly sees that you mean the numbers from 1 to 100, all of them, right? And so that means you quickly tell the reader what you're saying with writing less, okay? And this is one example of how notation is much better than no notation, right? Your first thought when you see mathematical notation is that this is silly. You see all these weird symbols when you could easily just write down a sentence, right? You could write, if you wrote more, it would be more easily understood. But Learning mathematical language is like learning a language of its own, but once you learn it, it's much easier, right? If you don't know what someone's saying, it's hard, but once you know what someone's saying, it's easy. So here's another set I, and so you could say the set of all I such that I is a positive integer. Okay. This vertical line means such that. I mentioned this before. So, and so this set is describing all the positive integers. Okay. So this is the set of positive integers. Another way to describe this set would be the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, ... Right? So there's infinitely many objects in the set, but you can concisely describe it as being the set of all I such that I is a positive integer. Okay, so these are examples of sets and notation used to describe large sets in a very concise way. Okay. The second thing to know is subsets. Okay, so definition of a subset. A is a subset of B if every element in A is in B. If A is a subset of B as sets, then we write this is the notation for it. I'll just use the okay, so A is a subset of B. That's what this is what we're talking about here. A is a subset of B if every element in A is in B. If A is a subset of B as sets, then we write this notation. So this is the notation that says A is a subset of B. Okay. I'm going to go to the whiteboard for a second. So if you have a set A denoted by this circle, right? And then you had a larger set B that contained it. This would be illustrating that A is a subset of B. Because when you put an element here in this Venn diagram, it would be inside the circle A to denote that it's in the set A. But any object you put, anything you put in this set A, like if I put the number 1 in the set A, it's also in the larger circle B. So every element in A is in B. And so that means that this is illustrating the fact that A is a subset of B. See that? And then if I put another element 2 here in the set A, I would also be putting it in B. So every element in A is also in B. And so this is illustrating how A is a subset of B. Okay. So Venn diagrams are very useful in describing relationships between sets. And so that relationship is one being a subset of the other. And so it's illustrated that way. Okay. So let A, B be outcomes of the same experiment. A is a subset of B is equivalent to the occurrence of A implies the occurrence of B. Okay. Right. So, right. So let's say the experiment. Let's say the experiment was, again, rolling a fair 6-sided die and recording the value on the top of the die, right? And so let's say the outcome A was the outcome of rolling 1, 2, or 3, well, let's say the outcome B was rolling a 1, right? Then that would mean that the occurrence of B implies the occurrence of A, right? And so the letters themselves are not what's important. It's the relationships that we're studying here, right? So if we reverse the roles of A and B, then you reverse the letters in the description, right? So here, A is 1, 2, and 3, and B is just the set contained in number 1. And so, here, the occurrence of outcome B implies the occurrence of A, because if you roll a 1, that means you rolled a 1, 2, or 3. Okay, and so here, B is a subset of A, right? And it also means that the occurrence of B implies the occurrence of A. So you can think of it as one or the other. Okay, so another example. Okay, so from example 1.1, that was the one with 36 ordered pairs, right? Ordered pairs, roll a red die, then green die, right? That one. So from that example, let's say the event B is, let's say the event B is a sum of 11. Let's say E is a sum of at least 11. Okay, then how would we describe the outcome B? If it's a sum of 11, well, you could roll a 5 first and then a 6 to get 11, or you could roll a 6 first and then a 5 to get a sum of 11. But E, the outcome E would be a sum of at least 11. And so a sum of at least 11, well, that means that the sum, and so that means the sum is 11 or 12, right? Because you're rolling 2 dice. So the most it could be is 12, but it could be 11. So 5 plus 6 or 6 plus 6, right? So E, a sum of at least 11 would mean you'd still have 5, then 6, or 6 and 5, but you could also have 6 and then 6. So these would be the outcomes of the outcome of a sum of 11 and the outcome of a sum of at least 11. Okay, and so the occurrence of B implies the occurrence of E, right? Also, B is a subset of E, right? So you see how you could say either, right? B implies the occurrence of B implies the occurrence of E, or B is a subset of E. Okay, so that's the
Professor?
description about subset. Is there a question? Someone has a question?
Yeah, I have a question about the subset sign. Shouldn't
Okay.
there be a line underneath, since every element of one set is within the other set?
Right. So when it comes to notation, right, it often depends on who's using it, right? So there's not necessarily one convention for subset. One way to describe subset is like this: A is a subset of B, right? And then if it's a proper subset, which I think you're thinking about,
Yes.
you would then say, okay, well, it's not equal. So then you would put like a slash over the over that. Let me just. So then you would have like a line, right? That would mean proper subset. That would be one way to illustrate sets. Another way would be, okay, well, A is a subset of B, like that.
Yes.
And then, I guess without a line, sometimes it's proper subset, but then I guess the way I would teach, maybe still use a verb. So that would be another way to do it, right? It depends on different books will give you different notation. Different people will use different notation. It's not like one. There's no one agreed upon convention here. So what I'll say you should do is you can use this notation or this notation to mean subset, just so we're all clear, and then this for proper subset. So with the line across the bottom part.
But isn't there like a difference between the two signs above? Like the left one usually means that there is a difference in one of the elements, like one element is not in the other set, whereas the other one on the right, every single element is within the other set.
Right, but
I
what
don't
I'm
know.
saying is right. What I'm saying is don't worry about what matters is the idea, not the notation. Okay, so
Right.
right. So the reason why I'm saying that is because while a lot of notation is agreed upon and everyone uses the same notation, there's some notations that are just not universally used. So that happens for subsets. So you probably learned in class, right, that this means proper subset. It sounds like with
Yes.
this, right? And so right now, in some people will use that as proper subset. Other people will not use that as proper subset. They use this subset. Okay. But what matters is the idea, right? So what I'm saying is that I'm using this to mean subset. I'm also using this to mean subset. And when I'm talking about proper subset, it's with the line here.
I see. Makes sense.
Make sense?
Thank you.
You're welcome. Okay, so that doesn't make it worse for you, because I think that if you are exposed to different ways of saying the same thing, it should actually help your comprehension of something, right? You don't want to be, right? So it's just, you understand what a proper subset and a subset is, right? And so, right, if you were interested in the field of mathematics, if you go in the real world, if you talk to one person, they'll use one notation. If you talk to somebody else, they use a different one. So, yeah, so the red is what I'm using to mean subset, and blue I'm using to mean proper subset. Okay. Okay. Very good. Okay. So okay, so that was so we were just doing subsets. So next is union. Definition. The union of sets A and B, written as A union B, is the set of elements belonging to A or to B. Elements in both sets are included in the union. Okay, so this is the definition of the union of sets A and B. The union of sets A and B, written with that notation, is a set of elements belonging to A or to B. Elements in both sets are included in the union. Okay, so I'm going to go to the whiteboard again, but I'm just giving you a second to read it or write that down. But the notes are going to be online, so you can get that again if you missed that. Okay, so let me go to the next page. So we used a Venn diagram to represent subset earlier. You can also use it to represent a union of two sets. And so so here I'm describing, I'm just doing it all by hand. Okay, so you have one set, that's a circle. You have another set, and so here's the universal set U. Okay, so let's say this is set A, and this is set B. Then let's go purple. Then the region purple, that represents A union B. Okay, so here, this is a description of A union B using sets, using Venn diagrams. So the intersection is here, right? And that's part of the union. And so that's what the definition is saying. The intersection, the elements in both sets is in the union also. Okay, this consists of all the elements in A or in B, and that also means all the elements in both. So that's A union B. Okay, good. Okay, so that's the definition of the union of two sets. So the outcome A union B occurs if and only if the outcome A occurs or the outcome B occurs, which includes both occurring. Okay, so the outcome A union B occurs if and only if the outcome A occurs or the outcome B occurs, which includes both occurring, right? And so here's the question you're probably asking yourself: what does if and only if mean, right? And so that statement involves saying the words if and only if, right? And so the answer to that is if and only if means, let me put statement 1, if and only if. Statement 2 means that statement 1 and statement 2 have the same truth values. Okay, so what does if and only if mean? Statement 1, if and only if statement 2 means that statement 1 and statement 2 have the same truth values. Okay, and so an example of if and only if would be, would be the statement, it is going to rain outside, or it is going to rain outside if and only if it is going to be wet outside. Okay, so it is going to rain outside if and only if it is going to be wet outside. So, and so this is one statement. It is going to rain outside, and it is going to be wet outside is another statement. Okay, so it is going to rain outside if only if it is going to be wet outside. So these are two statements I underlined. And so the if and only if is telling you that they have the same truth value, meaning it is both going to rain and is going to be wet, or it is not going to rain and is not going to be wet. The statement is not telling you that it's going to rain. It's not telling you it's going to be wet. It's not telling you it's not going to rain. It's not telling you it's not going to be wet. It's just saying that these two statements will either, these both things will either both happen or they both won't happen, right? Right, so they're tied together, these two statements. And so it's a statement about the relationship between two statements, not about the truth value of the statements. That makes sense, okay? So it's saying these two things will both happen or they both will not happen. That's the relationship between these two statements, okay? So it's a little bit more advanced of idea. Usually you think of statements as either being true or false, not both. This is an idea where instead of saying something is true or false or not both, it's saying that two things are either both true or both false. Okay, so so that's what if and only if means. And so the if and only if here is saying that these two statements go hand in hand, that they both happen or they both don't. And so the outcome A union B occurs is equivalent to the statement the outcome A occurs or the outcome B occurs, which includes both of them occurring. Okay, so it's telling you that A union B occurs when A occurs or B occurs or both, right? It also tells you that if A or B occurs or both, then A union B occurs, right? So, and They both happen. Okay, so if you know one of the two things underlined happens, then the other thing that underlined also happens. Okay, so this is the point I want to make, that sentence there. Okay. So a lot of statements that we'll be using in this class will use, at least some will use if only if, and so it's important to know what if only if means. And so I'm actually going to put that in a thing like this also. It's a tangent from the material, but it's something you need to know in order to understand the material. So just like the 52 card deck, where I put that line in between, this is just a small separate discussion that's important to know. And so now we come back, and so now you understand hopefully what this means. If you understand, this is my explanation of this. Okay. Okay. Okay, so that was union. So the fourth thing is intersection. So another definition. The intersection of a set capital A with set capital B, written as A intersection B, or another notation is also just AB, like you're multiplying them, but you're not multiplying its intersection, is the set of elements belonging to both A and B. So the intersection of a set A with B, this notation, or this notation, is the set of elements belonging to both A and B. Okay, and so a way to describe that with a Venn diagram would be, this is the universal set. This is set A. This is set B. And so what we want to describe is the intersection. And so the intersection would just be the elements in both sets. So that would be A intersection B. Okay. And so this Venn diagram is illustrating the relationship between sets A and B, and saying this set A intersection B there. Okay. Okay, good. So that's that. So let's look at this experiment. Oh, no. Okay, good. Experiment. So let's say the experiment is rolling 2 dice. Okay, so the outcome D is double, is the outcome of rolling a double. And so rolling a double just means that you roll the same number twice. So you could either do 1, 1, 2, 2, 3, 3, or 4, 4, or 5, 5, or 6, 6. Okay, and then the event F is sum of 4. So that just means you roll 2 dice, and after you roll 2 dice, the sum of the 2 rolls is a 4. So you have 1, 3, you have 2, 2, you have 3, 1. Okay, but I want the quotations here. Very good. Okay, so quotations are there. So you see those 2 outcomes right there, right? Good. And so the question is, what would be D intersection F? The intersection F is the intersection of those 2 outcomes. It's just the things that are in both sets, right? So you see here that this is in both sets. The 2, 2 is in both sets, and there are no other things in both sets, right? These are doubles, and here there's only 3 things, and 2, 2 is the only double. So the intersection of two sets is just the elements 2, 2. Right, it's a thing that's in both, the only thing that's in both sets. Okay, so that is intersection. The fifth thing is complementation. So definition, a complementation is a set operation applicable when dealing with a universal set consisting of all elements under consideration. If capital S is the universal set, then A prime is the set of all elements in the universal set S, not in set A. Okay. So a complementation is a set operation applicable when dealing with a universal set consisting of all elements under consideration. If S is the universal set, then A prime is the set of all elements in S, not in A. Okay, so I'm going to leave that for a second, and then we'll go to the Venn diagram. When you see the Venn diagram, it's very clear. Let me go to it. So again, I'm drawing the universal set. Okay, so again, I'm drawing the universal set. The universal set is the set of all elements under consideration. Okay. So here we're calling the universal set S. So let me put an S here. Okay, so that kind of corresponds with sample space, right? So for instance, if you're rolling one die, the sample space would have the numbers 1, 2, 3, 4, 5, or 6, right? That would be all the things you're considering, right? Okay, so all the things we're considering is a universal set. If you draw the set A here as a subset of the sample space as an outcome, then all the elements not in the set A make up the complementation of the set A. And so I'm going to label this as this. So everything outside of the set A, everything not in set A, but still something we're considering, is in the complement of A. So this is A prime, the complement of A. Okay, so this Venn diagram is illustrating for you the idea of the complement of an outcome. Okay, so let's say again, let's say we have the experiment. Okay, rolling a fair 6-sided die, and you record the face and top side value, right? So let's say the outcome A is the outcome of rolling an even number, right? Then A prime, the complement of A would just be not rolling an even number. Or you could say it's rolling an odd number. Or you could say it's the set 1, 3, 5, right? Because the universal set S, here, the universal set S is just the numbers 1 through 6, because those are the only numbers we're considering. And so A prime are all the numbers not in that set, right? This set is only the numbers 2, 4, 6. And so in the universal set, but not in set A, would be 1, 3, 5. Not rolling an even number, rolling an odd number, or 1, 3, 5. Okay, so that's illustrating the complement of a set. All the elements in the universal set, but not in the original set you're talking about. Okay, and so we're going to stop here, and so I'll see you tomorrow. Okay, so you're all marked here for present for the semester. We're done taking attendance, and I'll see you tomorrow. Thanks for coming today. Bye. You too. Have a good day. I said everything will be posted online, so if you can't see it on Blackboard, it'll be on YouTube. See you tomorrow. See you tomorrow morning at 10 a.m. Same link. You too. Have a nice day. Bye.